Hello friends, the next topic of MOS capacitor is the threshold voltage. Threshold voltage is one of the very important topic of MOS capacitor. There can be numerical 2 marks numerical in gate in coming year itself. Here, before I start with the threshold voltage, I will be flat band voltage. The flat band voltage is the voltage required to flatten these bands at the oxide semiconductor interface. This is the energy diagram of the MOS capacitor. This is metal side, this is oxide, this is semiconductor. In normal MOS capacitors with P substrate, the work function of P substrate is more than the work function of metal. The work function of silicon with P substrate with acceptor type of impurity is more than the work function of metal here. What is the work function? Just revision of that. Work function is nothing but that is the energy required to move an electron from the Fermi level to the conduction band. This is conduction band of the oxide. Work function is energy required to move the electron from the Fermi level to conduction band of oxide. In normal case, we don't define work function like that. In normal case, we define the work function as the energy required to move an electron from the Fermi level to the vacuum level. That means outside the surface of the metal. But in case of MOS capacitor, the work function is defined in another way. Reason being, when you connect this capacitor to some external voltage source, what could be the possibility? The possibility could be that electron from the metal can come to the oxide. When electron from metal come to the oxide, that will be jumping from the Fermi level of metal to the conduction band of oxide. In oxide, electrons will exist in the conduction band. In metal, electrons are supposed to be existing at the Fermi level or below the Fermi level. Similarly, so energy required to move the electron from Fermi level of metal to the conduction band is nothing but work function of the metal. That is how we define. Similarly, there may be the possibility the electron from P substrate to move to the oxide. That is nothing but work function of the semiconductor. And that work function will be defined as the energy required to move the electron from Fermi level of the semiconductor to the conduction band of the oxide. That is how we define the work function. But there is some new term which is known as electron affinity. What is that electron affinity? Electron affinity is nothing but energy required to move the electron from the conduction band of semiconductor to the conduction band of oxide. That is known as electron affinity. Here, at the interface between oxide and semiconductor, that is this boundary, this level. So energy required to move the electron from this level to the conduction band of oxide is known as electron affinity, and that is denoted by this Q xi or Qx, whatever your notation you have, right? You can say Qx, you can say Q xi. That depends on the symbol you are using. Now, here, the work function of semiconductor, that is from here to here, is more. You can see work function here is less, work function here is more. Because of that difference in the work functions, a voltage will be required to be applied across the capacitor to make these bands flat at the interface, to flatten these bands and to make this as flat like this. A voltage is required to be applied across the capacitor. That voltage is known as flat band, and flat band voltage is negative for MOS capacitor with P substrate. Right? Now, before I go with the expression in detail, let us voltage applied. when you apply positive voltage at the gate terminal like this, this is the gate voltage, positive at the gate, what will happen? The positive voltage at the gate will decrease the energy level of electrons in the metal. How? When you give or positive charge closer to an electron, electron will be attracted towards the positive charge. When electron moves closer to the positive charge, its energy level will decrease. And other way around, when you bring electron closer to the negative charge, its energy will increase. Here, I am assuming there are electrons in metal, you are connecting to the positive terminal, so energy of electrons in the conduction band, energy of electrons in metal, you can say, will decrease. Energy in not in conduction band, here it is Fermi level. So Fermi level on metal side will shift down. So new Fermi level will be here instead of whatever you are showing, right? And this fall in Fermi level is how much? Q into Vg, that is the energy, right? So if it falls down, so this will also fall down and this will also fall down. Reason is why? Because the work function will not change. Work function of the metal will remain same. So there will be bending in the conduction band of oxide at the interface between metal and oxide like this. So new Fermi, this will be the bending, and this is how much bending? That is Q into Vg. And why I am saying like this? Because this is energy, and similarly here it will be Q into V naught x if you take in terms of energy. It's not voltage, now it's energy, right? So there is bending of the voltage, that conduction band here. Similarly, because of this additional voltage applied, there is an additional electric field which is directed from here to here. From metal is positive, electric field will be directed from metal to the semiconductor like this. Why? Because this end is positive and electric field is directed from positive to negative. So electric field will be like this, from metal to the semiconductor, towards the semiconductor, you can say, right? Because of this application of energy, because of this positive charge, the electrons from the holes from this region will be repelled away. When electrons are repelled away, that means concentration of holes will be not electrons, the holes in this region will be repelled away due to this electric field. Electric field will repel away. When electric field is directed towards hole, the holes are repelled away. Holes will be repelled from this region. So in this region, the lower level of the valence band will shift downward like this. Why? Reason being because concentration of holes is reducing near the interface between oxide and semiconductor. When concentration reduces, so from the Fermi level, right? And similarly, there will be similar fall will be observed in what? Similar fall is observed in the intrinsic level. Similar fall will be observed in the conduction band, maybe like this. So this was Q S naught earlier, now this will become Q phi S, maybe like this. So what has happened? My voltage drop across the oxide, which was Q V naught X naught earlier, has increased to this much level. What is this level? This is V naught X now. That is what you have. So the applied gate voltage, if you see, the voltage applied across the gate Vg is equal to what? That is resulting into change in voltage across the oxide layer. And potential, earlier it was Q phi S naught, now it has become Q phi S. Earlier voltage across the oxide layer was Q naught X naught, now it has become Q V naught X. So that change in this and change in this will result into the change in the what? Change in the voltage, overall change in the voltage at the gate terminal. or we can say not gate, that is equal to the voltage applied. So the gate voltage Vg will be equal to change in voltage across the oxide layer, that is resulting into change, plus change in the surface potential, right? So this gives gate voltage applied is equal to V naught X is the final voltage minus V naught X naught was the initial voltage, plus what is there, Q, not Q, I will be taking potential, I am not taking energy, I am taking potential here. So that is phi S minus phi S naught. That's what you have. Overall change, overall applied voltage is resulting into change in the voltage across oxide layer, change in the surface potential. So that's what you have, right? So here this will be giving me the applied voltage equal to, that is this gives me V naught X plus phi S minus of what, V naught X naught plus phi S naught, and instead of this is giving me gate voltage Vg is equal to, that is what, V naught X plus phi S, and this is known as the flat band voltage. Here, although it is not flat band voltage, it is defined as minus of phi ms. It is known as the energy function difference, right? So this is Vg is equal to V naught X plus phi S plus phi ms, right? Or applied gate voltage Vg is equal to V naught X plus phi S plus phi S, then what, plus flat band voltage VFB here, right, where VFB is nothing but equal to phi ms, and that is known as flat band voltage, right? We have seen this expression earlier in my previous video. Now, so from here what I find is, I am able to find the gate voltage Vg is equal to V naught X plus phi S plus VFB, that is flat band voltage. This is very important expression, right? If oxide layer has fixed trapped positive charge, how much, positive charge of Qx, then what is flat band voltage? So that flat band voltage will not simply equal to phi ms, that will be equal to minus Qx by C naught X plus phi ms. I have given that expression earlier as well. So this flat band voltage may change if there is charge stored, charge trapped in the oxide layer, that flat band voltage can change now, but expression of gate voltage will remain same, right? So here there are some points to be remembered. The positive trapped charges in this oxide layer result into increase in flat band voltage. The flat band voltage becomes more negative because of the positive charges stored in the oxide layer. Now there may be the condition here, what has happened, because of the external voltage applied between gate and substrate, there is change in the voltage across the oxide and the change in surface potential, right? That's what we observed. But when this fall in this surface potential is nothing but 2 times phi f, then there is fall of the surface potential intrinsic level below EFS, or I'll say, I repeat, when intrinsic level of the semiconductor falls below the actual Fermi level, what will happen? This conduction band comes closer to the Fermi level as compared to the valence band. When, I repeat, when there is a limiting case, when phi s is equal to phi f, or you can say when phi s is less than phi f. Phi s is what? Surface potential. When surface potential from here to here is less than phi f, this intrinsic level is above the actual Fermi level. So when intrinsic level is above actual Fermi level, material will behave like p-type material. But there is a condition. When this surface potential phi s becomes more than phi f, what is phi f? Phi f is nothing but potential difference between intrinsic level and actual Fermi level. So when this surface potential, which is nothing but bending of the intrinsic level at the surface, bending of intrinsic level at the surface, or you can say the potential difference between the steady state Fermi level, which was this, and the actual Fermi level at the surface, that is known as surface potential. So when surface potential becomes more than the potential difference between EI and EFS, this intrinsic level at the boundary falls below. When phi s is more than phi f, this will fall below the actual Fermi level. So when intrinsic Fermi level at the surface of the oxide and semiconductor falls below the actual Fermi level, your valence band, conduction band will become closer to the actual Fermi level as compared to the valence band. And when conduction band is closer to the Fermi level as compared to valence band, the material behaves like n-type. So at the boundary in this region, your material is behaving n-type because concentration of electrons is becoming more than the concentration of holes in this region. In this region, rather than that's in this region, but in this region, right? So that is known as inversion of nature of material from p-type to n-type. But there is a threshold condition. What is the threshold condition? When phi s is what? That is fall in intrinsic level from the steady state level to the actual level at the surface. That is known as the surface potential. When surface potential, that is fall in the intrinsic level at the surface, is twice of the potential difference between EI and EFS, is known as threshold voltage. So I repeat, when the surface potential becomes 2 times the potential difference between intrinsic Fermi level and actual Fermi level, then the gate voltage is known as threshold voltage. So that is known as threshold voltage, and that is known as the threshold condition. Threshold condition for the device to behave like what? Device to work in inversion mode, you can say, and that is known as strong inversion mode. So I repeat, when gate voltage is equal to threshold voltage, phi s is equal to 2 phi f. So the threshold voltage is equal to V naught x plus 2 phi f plus V flat band voltage. So this is very important relation. Please do remember this. This is very important relation. Please do remember this. This is very important relation. Please do remember this. Right? So threshold voltage is the boundary at which the device is at the verge of entering into strong inversion. Strong inversion means what? The concentration of electrons at the boundary after this stage will become more than the concentration of holes in the bulk of the substrate. That is known as threshold condition. So please remember one thing, I have already given you the expressions. the flat band that is your energy for difference between, not energy potential difference between intrinsic and actual Fermi level is given by kT by Q, then natural log Na upon Ni. You can see my previous videos, I have already given that. So by putting this here, you can get all the expressions. But there is important point, one more important point. At threshold, your width of the at threshold, width of the depletion region, that is nothing but this is known as depletion region. So the width of the depletion region is maximum, and width of the depletion region will not increase beyond that if you increase the gate voltage. The maximum possible width of the depletion region you are going to get is W max. After that it will not increase. So at threshold, the maximum width of the depletion region is given by, that is equal to, that is 2 epsilon s, that is nothing but epsilon s is per into Q 1 by Na multiplied by, what is that, phi s. And you know what is phi s at threshold? What is the value of phi s at threshold? That is 2 times the potential difference between intrinsic Fermi level and actual Fermi level. So you get the maximum width of the depletion layer here, right? Now charge stored in depletion layer at threshold. Remember, before threshold we do not consider the inversion charge. What is inversion charge? That is nothing but electrons in the interface, electrons at the interface between oxide and semiconductor. Before threshold we don't consider the concentration, even though there are electrons. But after threshold voltage, I will be assuming the inversion layer of electrons at the interface between oxide and semiconductor. So at threshold we will not consider the charge due to electrons, that is in the inversion layer. Basically there is formation of the depletion layer here. That depletion layer will be having what? The depletion layer will be having, there is formation of depletion layer like this near the oxide semiconductor interface. This depletion layer has what? This depletion layer is free of holes and it has the negative bound charges of the acceptor impurity and electrons. Electrons will exist only when their surface potential becomes more than the potential difference between intrinsic and actual Fermi level. Electrons will exist only then. But we will not consider those electrons until or unless your surface potential becomes more than twice the value of the potential difference between intrinsic and actual Fermi level. We will not consider these electrons. We will be considering electrons only after threshold voltage. So for threshold voltage, we will not consider these electrons. So at threshold, the charges in the depletion layer is what? Because of the bound charges only. And those, that charge, or not only charge, I'll say charge density in the substrate at threshold is nothing but, this is charge density. Remember, charge per unit area. It is not charge, it's charge stored. Although I'll say charge stored, but I'll say charge density due to stored charge, right? That is equal to charge of each impurity multiplied by concentration of impurity multiplied by width of the depletion layer, and at threshold that is maximum, right? This is sometimes I'll be maybe denoting it by QD. QD stands for charge in the depletion layer, right? So now, what is the voltage across oxide? So voltage across oxide layer at threshold, that voltage will be how much? That voltage will be V0 x equal to voltage, that is charge density on the metal, divided by the capacitance of oxide. Assumption is there is no charge stored in the oxide layer. That is my assumption, right? And to maintain, there is important here, important point, to maintain the charge neutrality. What is that? I'll explain that. To maintain the charge neutrality, remember, as whole of the material is neutral. Total positive charge on the metal will be equal to total negative charge in the depletion layer to maintain the charge neutrality. So Q gate plus QS, the charge on the substrate, is equal to 0. So what is QM? QM is equal to minus Q of S. So here I will be getting the voltage across the oxide, V naught X is equal to what? QM upon, that is C naught X, that is equal to minus QS by C naught X. And further I will rewrite it like, that is V naught X equal to minus Q, you can say NA W max by what? By C naught X. And what is C naught X? C naught X is nothing but capacitance of oxide layer per unit area. So this is equal to epsilon naught X upon T naught X. T naught X is nothing but thickness of the oxide layer. This is known as thickness of the oxide layer, right? So epsilon naught is the difference. Here I am considering permittivity of the oxide layer, not the permittivity of the semiconductor, right? And when I consider this maximum, I have already written, but just repetition of W max is what? That is 2 epsilon S by Q into 1 by NA multiplied by phi S, or that is 2 phi F. This phi S is the permittivity of the semiconductor, this is permittivity of the oxide. Just to explain that, I have written these expressions. So please do remember these formulas. These are very important as far as exam is concerned. There can be numericals on these formulas. So the threshold voltage, that is equal to minus Q NA W max by C naught X plus 2 phi F plus the flat band voltage. That is how you can write the expression of the threshold voltage. So this is very important expression. Please do remember it. There can be numerical. Right, nowadays there are many questions which are appearing from MOS capacitor 1. Number 2, it is not very much clear concept. The MOS capacitor is not understood by every student. So I am trying to simplify it to the maximum possible level so that you can understand the concept, and if you understand the concept, it is easy to remember all the formulas. Mugging up is not possible. Understand the concept. If you understand the concept, you will remember all the formulas. Fine. So this is nothing but threshold voltage. I hope the concept is clear, the expressions are clear, the formulas are clear, and their importance is also clear for the exam. In the next video, I will be talking about the gate voltage beyond threshold voltage. When you increase gate voltage beyond threshold, let us see what will happen. And then subsequently I will take the numericals on these concepts. Yes, I just have a request. Please, if you are understanding the MOS capacitor, then the expressions, the derivations, please do forward my share my videos with your friends, and do let your friends know about this topic, because most of the students are afraid of the MOS capacitor and MOSFET. And please mind, This is very simple topic. If you listen to my videos carefully, you will understand each and every concept of the MOS capacitor and MOSFET. And again, I ensure, I promise you will be able to handle each and every numerical from this particular topic. So thank you very much for watching the video, and wait for my next video to come. Thank you.